Hello everyone and welcome to the SAS Viya Release Highlight Show for March 2023. I'm Stu Stukowski, a product manager for Visual Analytics here at SAS, and I've been interviewed on this show before to talk about the augmented analytics capabilities of Visual Analytics, and now I'm jumping in here to host for Tiago while he's out on vacation. I am a huge fan of this show, and it is so awesome to be here with you all. Let's get right into it. On today's show, we'll get the latest on SAS computer vision and image classification with SAS's Robert Blanchard and Neela Venkateshwaran. You'll also get to meet Dr. Taco, our fluffy star of the show. For our Release Talk segment, we'll talk with Mary Osborne about BERT models and how to use text analytics on SAS Viya. Well, let's turn it on over to Robert, Neela, and Dr. Taco to see what they've been working on with SAS computer vision.
Hey everyone, I'm Neela Venkateshwaran. I am a data scientist at SAS, and
I'm Robert Blanchard. Today we want to talk to you about how we used a multi-stage computer vision model to improve predictions on high-resolution imagery. In computer vision, resizing an image to a low resolution is common before we apply a computer vision model. We primarily do this to reduce the computational burden. However, this practice also allows practitioners to leverage weights from models trained by others who've trained their models on enormous data sets. In many cases, resizing an image to a smaller resolution isn't detrimental to the performance because the entity of interest is rather pronounced within the image frame. For example, let's say you take a picture of your family on holiday. It would be fairly easy for a computer vision model to identify your family members in the image. But what if you needed to identify if there was a minor teeny tiny imperfection on a shirt of a family member? When you resize the image, it is likely you'll lose the information that defines that imperfection. Now, this is a silly example, but the challenge of applying computer vision models to high-resolution imagery is real and is experienced across industries.
speaking of that, Robert, something that comes to my mind instantly is a pertinent use case that I find very relevant in the utilities sector, where we have some of our utilities customers flying drones over power equipment lines in order to do predictive maintenance. And this problem is pretty challenging because of the exact reasons that you just mentioned, where some of the assets that our customers are looking at, for instance, are insulators, and trying to determine if these insulators are functional or if they are defective. And these insulators become a very small entity of interest because of the distance and the different angles at which the drone captures these insulator positions. So there's really a need for us to come up with a robust solution that can overcome this challenge.
And that's what we did. We solved the problem by breaking it up into several stages, where in each stage we apply a different computer vision model. For example, in the first stage, we applied a localizer, such as a YOLO model, to a low-resolution image, just as you would for any object detection problem, with one exception. We removed the classification task from the model's objective or loss function to improve the model's localization performance, meaning the model doesn't know what it's putting a box around. It's just focused on putting boxes around essential regions where the entity of interest might exist. We then mapped the bounding box coordinates back to the high-resolution image and cropped out that region within the bounding box. These cropped images were then passed to the next computer vision model, which specializes in classification. This second stage model, the classifier, is trained on classes associated with the problem at hand, plus one additional class, which we refer to as an NA class. The NAs can be images of anything except the classes of interest. If the second stage model predicts a cropped image to be an NA, we remove the bounding box values from the final output. Ergo, the second stage model is used to correct the localizer's misses, in addition to predicting the classifications. And remember, the classifier is doing all of this from a high-resolution extraction, which isn't a computational burden because the high-resolution extraction is just a small fraction of the high-resolution image. Neela and I co-developed this approach where I use SAS programming.
And myself being more of an open source user, I still leverage SAS's deep learning capabilities, but from the Python interface instead. And this is the beauty with SAS because SAS really lets users like Robert and I use the language that we are most familiar with in order to carry out our analyses, rather than making us learn a completely new language from scratch.
We're going to show you a simple example of this solution. In this simple example, my dog, Dr. Taco, is running around on the beach. There's a drone flying overhead that's taking high-resolution photos and video of him as he runs around. Our goal is to identify what kind of scarf he has around his neck. Let's check out the demo.
Here we have a Python Jupyter notebook on the left-hand side that I leverage to perform my analysis, while on the other hand, we have our SAS programming interface that we refer to as SAS Studio, which Robert leveraged to co-develop the models using SAS code. And as we go along in the demo, we will see how similar my code in Python and Robert's code in SAS look like, even though we are using two completely different programming languages. And this is all made possible because of the flexibility that SAS Viya provides. Now, as Robert mentioned, the objective for this project was to develop a multi-stage computer vision model to detect the color of scarf around Dr. Taco's neck. And so the final state could have one of these four different outcomes, which is determining if the color of the scarf is blue or green or white, or if there's no scarf at all around Dr. Taco's neck. As we look at tackling this problem, having to analyze this data poses a few challenges. The data comes from aerial photos and videos taken from a drone, as Robert mentioned earlier. But notice that in the high-resolution image captured by the drone, for example, in the first image, Dr. Taco, who's here, occupies a very small fraction of the entire picture, which highlights the difficulty of this detection task. In addition, the drone's distance from Dr. Taco is in constant flux and can impact the level of Dr. Taco's granularity, with farther distances resulting in blurrier representations of Dr. Taco like the one you're seeing here. Detecting Dr. Taco's state can further be complicated because of occlusions where Dr. Taco may not be fully visible at all, like the one you're seeing here. And there can also be edge cases where, for example, the scarf is present, but not around Dr. Taco's neck. In this case, we classify this image as no scarf and not blue scarf. Moving on to looking at the multi-stage models we developed, the first step was to create an object detection model to locate Dr. Taco within an image. For this, SAS Viya provides deep learning capabilities that we can leverage from either the SAS language or the Python language. This is the flexibility that we have. To leverage the capabilities from Python, we install and import an open source Python package that SAS has developed called DLPy, as you can see here. This DLPy package encapsulates all the SAS deep learning capabilities within a Python wrapper, so I have direct access to all the deep learning capabilities that I can now use from a Python environment directly. Whereas if I'm coding in SAS, on the other hand, we directly have SAS functions to leverage these capabilities. Here are some examples of the input high-resolution imagery taken from the drone, which we'll be using as input images for our model. In addition, we also have some sample ground truth labels that contain the location coordinates of Dr. Taco within each image. These coordinates are shown by drawing a rectangular bounding box around Dr. Taco. So we'll be using the input images along with the location coordinates as inputs for training our object detection model. Now that we have our inputs for the model, we go ahead and train our object detection model. For this, we'll be using the SAS deep learning function called DLTrain to train the model. As we look at the Python code, we are able to invoke this function because we've already imported DLPy. And if we look at the SAS code that trains the model, we see that we are still using the same exact DLTrain function with the same exact function arguments that was used on the Python side as well. This is the ease of use that SAS Viya provides, where we can easily transition from using one language to another without any change in function calls or without any change in using the parameters or the arguments, but only having some very minor differences in the syntax of using these functions because we are using different languages. In the train function, we can see some of the parameters we are using, like the usage of GPUs to speeden up the model training process, because otherwise it's going to be computationally expensive to train a model on a lot of data. Notice here how we plug in some very precise values for some of the model hyperparameters here. These values were obtained by leveraging a powerful SAS genetic auto-tuning algorithm. Hey Robert, can you provide more details on this auto-tuning method?
Sure, Neela. Let me navigate to the Autotuning YOLO model program. SAS Autotuning is used to search decision spaces. We're going to surface SAS Autotuning from the Solve Black Box action provided in SAS Viya. SAS Autotuning leverages a Latin hypercube sample, a genetic algorithm, and a generating set search, where the genetic algorithm performs the globalized search and the generating set search performs the localized greedy search. To use Solve Black Box, we need to break our code into code sets or code blocks. The first code block is the initialization code block. That's where we load up and prepare our data. Notice here, I'm ending the code block with an end source, and I'm beginning the next code block, the evaluation code, with a source. In the evaluation code block, SAS Autotuning is going to loop through this code block and identify decision variables that we planted in the code and change those values. For example, here in the code, we're searching for the best decision threshold value, the best IOU threshold value, and the best train IOU threshold value. Further down, we're also searching for the best activation function to use in the model. So we can search for the model architecture in addition to hyperparameters. Additional hyperparameters that we search in DL train are the beta 1, our beta 2, and our learning rate values. Below DL train, we have DL score, which submits our objective function back to Solve Black Box. In the decision variables section, we specify the decision variables, whether they're an integer or continuous, and their lower and upper bound values. That's the range we'd like to search between. Finally, we end with specifying the population size. That's the number of initial evaluations that we'd like to try. The n local sets the number of generating set search permutations. And the max generation sets the number of maximum generations for which will breed combinations from the population. Back to you, Neela.
So once we have the model hyperparameters locked in based on the method that Robert just described, we can go ahead and train our object detection model. So here we can see how well the model trained on our training and validation data. But another great benefit with SAS Viya is the ease of deployment. So once we are done building our model, we can easily save our model to a SAS format called A-store file, which we can later deploy at the edge, in real time, or in batch based on our business requirements. So here we are scoring our model on validation data to see how well the model is performing. And then now when we look at the predictions, we see that the model, which was actually trained on resized versions of high-resolution image, when we look at the predictions here, the predictions look very blurred or grained out. So there's a need for us to map these predictions back to high-resolution images, as Robert mentioned earlier. We do this by joining our low-resolution predictions with the high-resolution image table, and the resultant predictions, which looked much more blurrier before, look much more clearer and look of better quality. And here are some examples of other extractions made by the model on the high-resolution images after we did the mapping. But note here how the model also extracted some other parts of the image thinking that they were actually Dr. Taco, like patches of sand, for example. We provide these non-Dr. Taco crops as feedback to our next stage of model, which is our classifier model, by now adding a fifth category to predict called NAs, which will contain crops that are not Dr. Taco. This really helps in refining and improving our model predictions further. So once we have the input images categorized into these 5 folders, we do a similar model training process like we did for the first stage model. But now we'll be training a classifier model here, where the outcomes will be predicting the label as one of the 5 outcome states that we defined earlier. So here is the model training history that we have and how the model scored on some sample validation data. We see that the model performed really well with a misclassification of just 1.7%. With SAS Deep Learning, we can visually inspect our predictions. So here are some correct predictions that were made by the classifier model. For example, we can see how this image was predicted as a blue scarf and how this was a no scarf predicted from the model. There were also some rare mispredictions that we can inspect by looking at these visually. But one of the other highlighting features of SAS Viya is how it provides model explanations to understand why a model made a prediction a certain way. And this feature really helped us to better analyze misclassified images and make decisions as to how the model needed to be retrained. For instance, this was a misclassified image from the model. It was actually an NA, but the model instead predicted it to be a green scarf. So using SAS's model explainability feature, when we try to generate a heat map on this image, you can see how the heat map generates blue pixels within the image, which is where the model is exactly focusing on to make the predictions. So the model was indeed focusing on the green cup that this person was holding, which made the prediction to be a green scarf. So this feature was really helpful in making us understand the reasoning behind the model's predictions. And as usual, we can easily save off this model as an A store, and now we can deploy both these models easily to make some real-time inferencing. Robert, can you show us an example method in which these models that we develop could be inferenced in real time?
Sure, Neela. We use SAS event stream processing to take our computer vision models and deploy it on real-time video or streaming data. SAS event stream processing is very easy to use, and it makes deployment seamless. So here you can see the model is predicting the white scarf right as the white scarf goes around Dr. Taco's neck. Dr. Taco is running up and down the beach. The drone is moving. The angle is changing, but the model's performance is doing really well. So right here, I'm going to take the white scarf off of Dr. Taco. So you can see the model has now predicted no scarf, and the blue scarf is being placed around his neck, and the model is predicting blue scarf. So today we showed you how to improve your computer vision predictions on high-resolution imagery.
If you'd like to learn more, check out our blogs on the SAS Data Science blogs community available. Thanks for watching.
That is so cool. Well, as you can see, SAS Viya makes it easy to create image recognition models through multiple programming languages, all powered by the same in-memory analytic engine, SAS. Having end-to-end modeling and streaming capabilities on a single platform has a huge number of possibilities. You can use this to track robots in the production floor of a factory, or even detect car crashes with interstate cameras and improve emergency response times. You could even monitor the checkout area of a large shopping center and automatically alert management if checkout lines are becoming too busy, and much, much more. Well, that was Robert Blanchard and Neela Venkateswaran from the SAS Global Technology Practice. And of course, Dr. Taco, who has his PhD in archaeology and is a very good boy. Generative AI is the engine behind technology we're all hearing about nonstop, like ChatGPT. Generative AI has taken the world by storm and is used to create synthetic data, generate text, and even create artwork. In today's release talk, we are super excited to be talking with Mary Osborne about generative AI models, including BERT models and SAS Visual Text Analytics. Well, now we know that this is a complex topic with a lot of moving parts, so we're going to make this a two-part conversation. The first part today and part two is in next month's show. I give to you the release talk. Welcome, Mary.
Thanks, Stu. I'm happy to be here.
Well, let's get right into my first question. Something brand new from SAS is the release of BERT models. What are they and how can they be used?
BERT stands for Bidirectional Encoder Representations from Transformers. BERT's a neural network-based framework that's fantastic for text classification, summarization, and question answering. We're currently using it for classification.
You're saying that BERT models can help with classification. I know that classification is something that happens within text analytics and natural language processing. Can you explain how all those work together?
Sure thing. Classification is a method to categorize data. One common classification method is sentiment analysis, which gives us the ability to determine polarity, whether a document, tweet, or review, things like that, are positive or negative.
Well, classification is something that's not new to SAS by any means. So what's the difference between BERT classification versus other SAS classification capabilities?
SAS has had techniques for classification, including sentiment, for many years. Those techniques are rooted in symbolic AI, which is a rules-focused approach. BERT classification is a machine learning technique. Symbolic AI requires human intervention to write the linguistic rules for classification. Machine learning involves human intervention on the training side to ensure that you have good labeled data for the training of the model. Without appropriately labeled training data, the model won't predict well on new data. So there's a time and a place for each approach, and we offer the best of both worlds now. So let me show you with a quick demo. This is SAS Studio. What we're looking at right now is the data that I'm going to score as a part of my BERT classifier. The data is actually generated by ChatGPT. I asked it to generate some sample data for March Madness, and we could take a look at the polarity on it. You can see that there is, just by glancing at it, a decent mix of positive and negative. So what we're going to do is go into the code windows. So now we're looking at the code, and what we have is an action set called text classifier. So the first thing we're going to do is load that. The next step is to bring up the train text classifier action out of that action set. We can set a batch size, which is going to determine the number of samples processed at a time during training. We can set a chunk size, and the chunk size is going to determine the length of the input sequence during training. I've got GPUs enabled. It's always a good idea when you're running any type of machine learning, but especially the BERT classifier, to run these on GPU because performance will be significantly better. You can set your epochs, and that's where I have my max epoch set to 10. From there, we're going to specify the table that we're going to use for training. So I have a table here in my public library called March Madness Training. What that is it's a selection of data that's very similar to the data we looked at that we were going to score. Only in the March Madness Training data set, I have that labeled with the specific polarities of positive and negative. The model we're going to create is called sentiment model. The target variable is going to be sentiment, and that's the polarity that I've assigned as a part of the labels. And then we're going to assign the text variable to text, which is the actual narrative. We'll run that. That completes the training. And then we need to score the data. So in scoring, I'm calling the score text classifier action out of the text classifier action set. I'm going to create an output table called outsent March Madness. It's got a doc ID, which is just a unique identifier. The model I'm going to call is sentiment model, which is the model that I created up here. The table is public March Madness, which is the one we just looked at. And the variable that we're going to be running against is called text. And then you could add something like a table fetch at the end if you wanted to take a quick look at your output. But what I've done instead of that, I've actually gone into SAS Visual Analytics, and I built a really simple report. So in this report, I have an output. This is the output from the score. So in this report, I have a graph that shows me my positive and negative documents, and I can toggle them. Down below, I have the actual documents and the sentiment that was assigned using the text classifier action. So this is just my collection of just a few negative documents. So you've got things like, I can't stand March Madness. It's just a bunch of overhyped games. That may or may not be my personal opinion, but that doesn't matter. So I've got my text, I've got the sentiment, and the score. The closer that score is to 1, the more highly negative, in this case, a document would be. So if you've got data with significant polarity, you'll see those numbers creeping higher. If the sentiment is just sort of a little bit negative, then that number will be lower. And the same thing goes with our positive sentiment. So that's a quick walkthrough of the new text classifier action set in SAS Visual Text Analytics.
This is so exciting to see the innovation here. Now that we know the basics about BERT models and classification, how does this relate to ChatGPT? What are the similarities and differences?
Well, ChatGPT and BERT are both transformer models, but they're designed for different applications. As I mentioned earlier, BERT uses the encoder transformer architecture. That's what makes it great for classification, summarization, and tasks like question answering. While summarization and question answering do generate text, the results are based on extracts from existing information. The GPT models, ChatGPT included, are encoder transformer architectures. They're designed for novel text generation. Different architectures, different strengths. Another key difference between BERT and GPT models like GPTs 1, 2, and 3 and ChatGPT is they're subscription-based. BERT's open source, so it has a lower cost of entry for our customers. There is an open source implementation of GPT models called GPT-J. It has far fewer parameters, 6 billion versus GPT-3's 175 billion, and was trained on smaller data. GPT-J is really good at generating code because it was trained on GitHub and Stack Exchange data. They all have their pros and cons.
Transformer models have really changed the game with how society thinks about AI. This technology has a huge potential to change the way we work and live, especially when it comes to advanced analytics. Mary, thank you so much for joining us today. We look forward to talking to you again next month and dive deeper into generative AI. To learn more about the demo you saw today, SAS Communities is a great place to start and connect with Mary. Well, we've reached the end of this month's show, but we'll be back at it again next month with more guests and highlights. If you're watching this on YouTube, why not give us a like and subscribe to the SAS Users YouTube channel and click that bell so you'll be notified for new videos when we go live for our next show in April. Until then, comment on what topics you'd like to see in future shows. It's been wonderful to be here. I've been your host, Stu Stukowski. Tiago will be back next month, and I am so glad I got to jump in. Thanks, everybody, and stay sassy, y'all.